Okay. Okay, thank you for coming to the seminar. I'm going to talk about something that's new to me, and I'm also trying to learn about it. Stabilizing machine-learned physical parameterization in hybrid climate modeling, and I will explain this later. My collaborators are Jianda Chen from Minghua University, Hao Zhang, Wu Yinling, Brookhaven, and Wei Xue from Minghua. Jianda did the heavy lifting, most of the work. He is a visiting student to the US, and here is the real story. While here, he went to Toronto to join a birthday party of a friend. When returned, he was stopped at the border. He was questioned for 4 hours. After that, he was returned to China. He was not allowed to come. So he went to apply for visa again. After 3 months, he came back. This is key word number 1. If you are an international student, just be prepared for the unexpected. So the brief talk would be, I try to phrase the problem, then the method. We developed some results and a brief summary, then ongoing research. So the problem, both numerical weather prediction and climate modeling can be schematically written as, say, a tendency equal to a forcing. If it's temperature, then it's a thermodynamic equation. If it's the wind, then it's a Newton's second law. And this forcing, we typically separate it into resolved scale dynamics and then physical parameterizations. The resolved scale dynamics uses the geophysical fluid dynamic equations, the thermodynamic laws, and the physical tendencies would include radiation, convection, turbulence. Some of these are subgrade scale, others could be grade scale. The prediction is basically to advance from a previous time, then the operator, then the next time. The machine learning methods are currently used to improve the model. And the reason is the models are not accurate, like the intense precipitation in Texas. They might be actually rooms to have the models better. Of course, data is another component, but a lot of efforts are devoted for improving the model using machine learning techniques. There are 2 types of machine learning models broadly categorized for prediction. One is for in our area. One is end-to-end modeling, that is train the whole operator, basically mapping the past to the future. You bypass the dynamics, you bypass the physics. In the simplest case, you can think of almost like a time series, use the past to project the future. Here, it's of course more involved because it's global, spatial with many variables. And this is the end-to-end. Another is the so-called hybrid modeling. The hybrid modeling is to calculate the dynamics based on the formulated equations that we think with relatively good certainty. Then the physical parameterizations are calculated through a neural network instead of physical parameterizations. And then in the actual prediction or modeling, the output from the neural network becomes the physics tendency. Combining with the dynamics, you proceed to the next step. So machine learning in hybrid modeling replaces the traditional parameterization by using neural network. So for the weather forecasting, the successful ones reported are primarily the end-to-end model, mapping the past directly to the future states. Looking back in the past before numerical weather prediction, the forecasters actually try to remember what happened in the past, then do the synoptic forecasting to the future. And the machine learning is somewhat similar, going back to the old method. However, it's using modern technique, and I think the cutting edge ones are the graph cast from the Google DeepMind's group. These are large groups of people, both from computational science and the atmospheric science. Then the forecast net by NVIDIA, Penguin Weather by Huawei, ClimateX, Microsoft. As you can see, all of these are bigger centers with computational resources. The forecasting skills are reported to be better than state-of-the-art of the ECMWF integrated forecasting system. And we know ECMWF represents the state-of-the-art for synoptic type of weather forecasting. The first three methods are being tested at major operational centers. The ECM AI system, a variant of the Google GraphGrass, went operational in February this year, and the ensemble forecasts started last month. So it's evolving fast. If you are interested in how they're doing, I have this link. Yes. So this is the ECMWF real-time forecast. You can click to get the map. Then screen down, you see AI forecasting system. You click it. These are from the AI side. So if you are interested to see the latest, then this is actually available. And it becomes part of their operational product. In their forecast, of course, the physics model is still the standard one. This is an area of intense research. For example, papers are published like every year in Nature. That looks like the next Nobel Prize in physics could be awarded to weather forecasting. All models need to use initial condition from data using the physics models. Now, so this is end-to-end models projecting past to the future in the short term. But for climate modeling, machine learning has its own problems. End-to-end modeling cannot account for the changing climate forcing, do not have enough training data. The second problem is if you use hybrid modeling, then it often encounters instability. Most of the time it's unstable. You integrate for several years, actually sometimes, most likely a few months, the model will just crash. And the reason is you train it, you get a physical parameterization, you have errors feeding into the dynamics. Coming to the next step, it cascade that would lead to instability. We have seen results published for long-term simulation, but these only used idealized setup like aquaplanet. The system is better behaved or by trial error methods. Some would crash, some would go. So now the method we worked out is published in this paper by Chen et al. And to describe it, I use two figures. The classic training method, you have the dynamics feed into the neural network as input, traditionally feeding to get the physical parameterizations. This model is going to be calibrated by using the ground truth data. And the ground truth data is the high resolution simulation from cloud resolving models using Murata's SAM. And the SAM model is really widely used in the community. Most of the climate modeling, machine learning training use this data set. That's Murata's PhD thesis research. So you have a good legacy is Murata here. Yeah. So now this training is kind of overwhelming to many people because a huge amount, very complex, millions of parameters, but we should try it to be simple. That is, you have an X input, you have an observed Y. X and Y, you can develop like a regression. But instead of a regression, it's a neural network. You don't need to know a lot about neural network. If you know Python, you just call a function, designate what model parameter, how many layers you want. And if you don't know which function, use ChatGPT. So this is available, and most of our students have learned Python. I very much encourage you at least to get a sense how this thing works, as long as you have data and then input and output. Okay, so now the method in our case is really to say you have the physics tendency from the neural network. What we did is consider the physics tendency the neural network calculates from a previous time step as input to the neural network, in addition to the input and the ground truth. The reason is the physics tendency should have continuity from one time step to another time step. The other is the errors from the neural network would be accounted in the training itself. If there is a large error, it contains a large error, but it would be constrained by the ground truth. And so what we found was that this method was quite robust when it's used in online calculation. This is the time variation of the global static energy. There is no drift. And this is the precipitation from different seeds global distribution. I won't go to detail, just to tell you reasonable. So the main purpose here is to get it stable first. And so now, just a summary, experience replay enables machine learning parameterization to recognize and correct its own errors. in the training. Once the training is done, like a graduate student, then you are on your own. You are going to do a free run in the model, but during the training, the errors are used. And the train conditions, the train is made under conditions resemble the actual online users. This leads to stable hybrid simulation. Lots of questions, bias, extreme precipitation events, etc., etc. The media range forecasting, and these are all up for research. I would imagine going into the future, we will try people trained in the domain, like in atmospheric science, would do research figuring out why the machine learning models cannot learn this phenomenon and what to do to make it learn better. So this is, I think, what people are actually working on. Thank you.
Almost out of time, but maybe a question.
Yeah, I think a lot of talk about the machine learning for climate is that you have to learn what you have under the current climate. So how do you do that? So you basically run the model in different climates and assume that the model is producing correct.
Yes, so that's a very relevant question. Here, it's just to make it stable. But for climate simulation, what we are envisioning is just to change the physical parameterizations. Therefore, when you run the cloud resolving model to get the ground truth, you can have the carbon dioxide also increasing at a different level. You run the cloud resolving model, then the ground truth is used to change the parameterization. And therefore, you can account for the changing of the forcing.
Yeah, maybe a follow-up question though. So in the hybrid approach, there's certain levels of, like, the dynamical cores are things that we actually have equations for that we, of course, can't solve perfectly, but and radiation is another one that has done pretty well in the model, where convection is something that we still struggle with. So how, when you're developing a hybrid approach, are you just replacing all of the physics parameterizations, or can you say, hey, we have a good physical understanding of these and they're relatively cheap compared to aerosols or something like that, make educated or expert judgment decision about what parameterizations to do?
Yes, very, very relevant question. So there are different type of studies. Some people just do parameterization, machine learning parameterization of the radiation code, which is more doable. Here, what we used was to replace the whole parameterization using machine learning. Now, one ideally could do like a part of the calculation using physics model like radiation, other part like turbulence or convection using machine learning. These certainly could be tried, but the one caveat is that you need the input data for the calculation of the radiation model, the clouds, the precipitation, and that becomes messy. Of course, one can learn these separately, then feed into radiation, and these are all up for research. Yes.
Do you know how well these models do with like extreme events? Because if there's no precedent for these events, then how would the model know like what to predict?
Yeah, I know the weather forecasting models that I highlighted, they do not do very well with extreme events. The only one that claimed to be good with extreme events is the Microsoft one, the Climate X, but Climate X has not published much and has not been used by the operation centers, while all other three are actually being used at the operation centers.
And these are only as good as you train them, and a lot of training at ERA5 type stuff. But we just need a reforecast effort, climate and weather to tackle this issue of streams. To have other data sets in.
Well, what kind of training data is it? Is it just column? Is
Yes, sir.
due to physics?
Yes, so it's 3 years of super parameterization, and then you train the model using all the grades, all the GCM grades. So the data set is quite large, and you treat the different columns as different sums.
So data sets like diamond would not be useful.
Dynamite would be useful. What you will need is to coarse resolution. Some people do that. The so-called dynamite is a global cloud resolving model, certainly better than you average the tendencies within a grid box.
Well, we're over and there's lunch waiting for us. So let's thank Minghua.
Thank you, everyone.